My name is Chris. I'm leading a team at Google building a system called TensorFlow Federated, or simply TFF, and I'm here to tell you about it. TFF is a new development framework for what we call federated computations. These are computations on data that is born decentralized, for example, on mobile or IoT devices, and stays on device where it was born. Federated learning is one example, federated analytics is another, and there's more. We're very actively using TFF at Google as a common foundation both for federated learning research and production deployment. And we'd like to evolve it together with you, with the open source community, to support use cases outside of Google. Now, what is TFF? You can think of it as having three major parts. There's a layer of new programming abstractions for the federated computations, for defining them, and I'll talk about this in a minute. On top of these abstractions, we have implemented various federated learning algorithms that are available through Count APIs, such as TFF learning. And finally, there is an extensible runtime infrastructure for simulations and beyond, and I'll cover that one in the later part of the talk. Now, I mentioned that TFF is a common foundation for both research and production deployment. TFF is designed to let you write code just once and then deploy it anywhere you want. So you can run it in a simulation locally in a Jupyter notebook. You can run it on a Kubernetes cluster across multiple data silos, whether it's within a data center or across multiple data centers. And you can also deploy it across a fleet of mobile devices. And so you have all this flexibility once you write your code. And to make it possible, to enable this, TFF defines a small internal programming language in which you express these computations. So any code you write in TFF is serialized into a platform-independent representation in that language to give you all those different points of flexibility, and I'll explain that in a minute. But first, let's demystify what those federated computations are. As I mentioned, those are computations on data you can collect. Very often for privacy reasons, there could be other reasons. Data that remains on devices that may wish to remain anonymous. And there could be very many of them. That has certain implications in the real world. Let's explore those. And let's explore them on the example to make it less abstract. And so imagine we have devices with temperature sensors. And let's imagine, for the sake of this exercise, these temperatures are sensitive data. Right, and now analyst on the server wants to know what fraction of the devices have temperatures above some threshold. Now, again, temperatures being sensitive information, we can't just go ahead and collect them. And so we have to push the computation to the devices, right? So first, we'll broadcast the threshold to some subset of those clients. And now that each client has the threshold and its own temperature reading, and they can compare them locally. So that's the local computation, right? A simple one. And output 0 if it's below the threshold and 1 if it's above, right? So this is, you can think of this as a map step in the map radius, a computation that runs entirely on the clients. Now, finally, with all these ones and zeros, all that's left to do is actually average them out and deposit the results on the server. And there goes, the ratio that we're looking for, right? And of course, if you have thousands or millions of clients, you may have to repeat this process many times. So in each round, that will involve a broadcast, a map, and aggregation. We would potentially be talking to a slightly different subset of those millions clients. By accumulating the results across many rounds, we can get a more robust estimate. So now getting back into the abstract. And so we have many, many rounds that can potentially involve different subsets of clients that, as I mentioned, may wish to be anonymous. They can disappear at any time. And we don't know if or whether ever they will be back, right? So we treat them all as pretty much interchangeable, essentially stateless, right? Because you cannot rely on that state. You never know whether you will get it back. And so here, all the operations in clients have to be done in collective, just like in MapReduce, right? There's really no place in this programming model, in this kind of a framing for manipulating individual client identities engaging in deliberate point-to-point interactions with specific clients, treating them individually. They're all just members of a collective. So in this model, the clients, as you see, do all the work, but the server also has an important role in orchestrating this entire process, aggregating the results. And of course, if it runs across many rounds, then carrying state over from one round to another as a subset of the device's changes between the rounds. Now, getting to the nuts and bolts of this, we introduced, as I mentioned, programming language that supports this. It has a distributed type system in which a value can be federated, as we call it, or distributed, so it can exist in multiple places. Temperature readings were an example of that, a value that was conceptually a single input, but that input existed in multiple locations on the different clients. Programs in this language are also distributed. In fact, the best way to think about federated computations is as little distributed systems, and the language we provide is a language that allows you to compose simpler distributed systems into bigger distributed systems, right? And these computations can have inputs and outputs in different places. So as you saw, our example had one input on the clients and one input on the server side, and that's okay, because again, it's a distributed system. And finally, the communication here is an essential part, integral part of this programming model and the language, not just some systems concern that's hidden underneath. Now, here's how you can express our example in TFF in an actual APIs that we provide. You start by writing a Python function, declare all the inputs and outputs wherever they are, so client side or server side. Now, in the body of the function, you can call the federated operators, and so you can see the broadcast, the map step that runs the clients, and the aggregation, just like in the example that you saw previously. And finally, the local processing can be expressed in TensorFlow in this case, although we've designed our system such that other options can also exist. Now, all this code you wrote is traced just once and serialized into the platform-independent format that I mentioned earlier. So the whole process is somewhat analogous to what you can recognize in graph mode in TensorFlow, right? When you use Python as a syntax to define the program logic, but the actual program logic isn't Python. It's serialized into a form different from Python that is platform-independent. Now, just so you have an idea of what the data structure is that represents the federated computations, here's what it looks like. It's purely functional. There's some lambda calculus in it and whatnot. Most importantly, I'd like to stress here that this platform-independent representation is designed to be extensible. So there can be other types of local processing that we can incorporate for different kinds of deployments. And those can be incorporated into this broader framework that includes the lambda calculus, federated operators, and various other compositional constructs, just like those that you saw on the previous slides. Now, as I mentioned before, we've implemented various federated algorithms using these abstractions, and we made them available via Cand APIs in TFF. And you can see examples of these in tutorials on our website. I won't dig into those. Just to give you a very quick example here, if you have a Keras model, it's a one-liner call to create computation that does federated training. Now, again, these are deployable anywhere you want, but for the sake of simplicity, if you just want to run a little simulation, you can also treat them just like Python functions and write simulation loops just like the one shown here. By default, if you do that, everything runs in a local TFF runtime that's transparently created under the hood for you in the same process. Now, you do have other options if you would prefer to run a distributed simulation, maybe for something larger. Again, we provide some Cand APIs that make it very easy for you to construct different kinds of runtimes. For example, there's a tutorial on our website that shows how you can run things on a Kubernetes cluster. And again, you don't even have to change your simulation at all. You just set up a new Kubernetes runtime, set it as a default, and run it as usual. It's very easy, just the same way you saw in the example before. Now, we provide Cand runtimes for, or what we call executors for several of the common scenarios. And so by default, you get one that runs locally and can be multi-threaded on CPU or GPU. You can also easily set it up to run remotely over the gRPC interface. So you can use our executor, or you can implement your own, set it up remotely and connect to it. And finally, as I said before, you can run things in a cluster, and you can set it up potentially as a multi-tiered system with several intermediate layers of aggregators for scalability. And all these different architectures are actually supported by the same very small set of components, all of which implement the same generic abstraction of an executor. So an executor is a basic unit of composition in TFF for constructing various kinds of architectures. And let me say just a few words about it. And it's basically a box. An executor is a box with data and some computations that run inside of it. It supports 5 basic operations. The first one is to push some value inside into the executor, some payload into the box. So here we're pushing number 10. In response, you get a reference, which you can think of as being analogous to a tensor pointer. These references have asynchronous future semantics. So the computation may be still running. In this case, it's just uploading a number, so it's simple. Functions are also values in TFF. So here we are pushing another value. This time it's a function that takes a number and adds 1 to it. And again, you can create one inside of an executor. You get back a reference. With the 2, you can create a function call. Now, again, you get back a reference to a result. And as I mentioned, it has asynchronous future semantics, and so that the reference will be returned to you before that computation potentially even started. And you can use it right away. So you can, you could form a tuple out of that and something else. You can make selections. And with all these basic constructs I've shown you so far, basically you can orchestrate arbitrarily complex kinds of processing inside of an executor, with graphs of cascading function calls. And the tuples and selections are here basically just so I can slice and dice results and move them around. And anything that's of interest, you can compute to retrieve from the executor, request the payloads, and potentially keep computing. And that's it. TFF provides a whole library of executors that specialize in different aspects of execution, such as multi-threading, or communicating over gRPC to some other executor, caching, processing lambda expressions, and whatnot. And all the different runtime architectures, from single machine to multi-layer distributed, are actually constructed from these small number of building blocks and composed in different ways. And so it's very, very modular. And this is designed to be extensible. And so here is actually, I want to thank our friends from Cape Privacy who have contributed new components to the TFF runtime to integrate with TF encrypted. We are extremely happy to see this, and I would encourage you all to read their blog post. Okay, this brings us to the end. I hope that you can also find TFF useful and potentially contribute as well. And here, our extensible runtime stack is where I'm particularly hopeful to see some good opportunities to integrate TFF with various parts of the OpenMined ecosystem. If you're interested in exploring this, please do reach out to us. We'd love to hear from you. And that's all I have today. Thanks very much.